Today we're going to look at maximum and minimum values. If you remember from Calc 1, that's another word for that is extrema. So you're going to learn how to find the extrema of functions of several variables. Remember when we did that in Calc 1, the way we did that was first of all to find the critical points. Remember that? And the critical points would be the point where the derivative was 0. All right, and then you had to test that critical point using either a first derivative test or a second derivative test. Okay, so we're going to do much the same thing, but of course it will be more complex. Right? First of all, let's get the definition of a local maximum and a local minimum, which is basically the same concept in for a function of one variable in single variable calculus. The local maximum would be the highest point within a neighborhood, within an interval, and same thing for the local minimum within an interval. That's why they call it local. So, a function of two variables, we're looking at two variables, okay, has a local maximum at the point AB if the function f of xy is less than or equal to f of AB for all points xy in some disk with center AB. So instead of saying a neighborhood, because we don't really have a neighborhood as such, we call it a disk. Just like we did limits, we use a disk, right? So here we're using a disk. F of AP is called the local maximum value. Similarly, for the local minimum, if f of xy is greater than or equal to f of AB within that disk, then f of AB is the local minimum value. Now what happens is that if these inequalities hold for all xy, it does not have to be in a disk, over the entire domain, then it becomes an absolute max or an absolute min. Recall another word for absolute is global. Let me write that. So you might see global. And another word for local is relative. Now let us look at the definition of a critical point. So remember, how did you get a critical point previously in Calc 1, where the derivative is 0? A point AB such that the first partials equals 0 or one of them does not exist is called a critical point. Thus, a critical point is a point at which del f is equal to 0 or is undefined. So we're going to find critical points in a while, but let's just go on because we already know how to find partials, put them equal to 0. We know that. So let's just go on to how you find local extrema. First of all, let's look at necessary conditions. And it says here, if xy has a local extremum at AB, so that is, if AB is either local max or local min, and you know that the first derivatives exist there, then the first partials at that point equals 0. Important point. So if you know there's a local max somewhere at a point, therefore you know that the partials at that point equals 0, the first partials. Now, this is important. This is not a sufficient condition. If the first partials at that point is equal to 0, it does not necessarily mean that AB is a local extremum. It could be a saddle point. Go back to single variable calculus. Remember we said the same thing. If the derivative at the point is equal to 0, it does not necessarily mean that it is a max or min. It could be a point of inflection. So in single variable calculus we had points of inflection, right? Now in multivariable calculus we have saddle points. And then we'll see what saddle points look like in a little while. So these are all definitions. So let's move on as soon as I can get where we're moving to. We're going to find some critical points and we are going to classify them. And when I say classify them, I want you to tell me whether these points are local maximum or local min. And we are going to do this basically by brute force. I would say by the first, I would call it the first derivative test. Okay? All right, so let's find the critical points. So the first thing we're going to do is to find the first partials, set them equal to 0, and solve. So the partial of f with respect to x is 2x minus 2. Put this equal to 0, and we get that x is 1. Partial with respect to y is 2y minus 6. Put this equal to 0, and we get y equals 3. So the critical point is 1, 3. Now let us find the value of f at that point, because that is important. F at 1, 3, put that into the function. 1 plus 9 minus 2 minus 18 plus 14, and that is equal to 4. Now, we want to determine whether this is a maximum or minimum. So we're going to see, in other words, what do the other points within that function look like? What are the values of these points? Now, we're not going to test all the points. I'm just going to teach you a little trick that you can use with the first derivative test. You look at the function and you tweak it a bit. See if you can write it in another form. Now, the presence of x squared and minus 2x, y squared and minus 6y tells me I can complete the square. So let's complete the square here. So I'm going to rewrite f of, okay, let me just write complete the square. Complete the square. So let's write f of xy. We'll just put the x's together. So x squared minus 2x. The y's together plus y squared minus 6y plus 14. Okay? Now we are going to complete the square. We are going to do it for the x's and then for the y's. Okay? So x squared minus 2x, what do we add to complete the square? Let me, 1, yes. So you divide the coefficient of x by 2 and square the result. So minus 2 divided by 2 is negative 1 squared, you get positive 1. Okay? Do the same thing for the y's. What do we add to the y's to complete the square? 9, beautiful. Divide negative 6 by 2 and square it. Then add the 14. Notice we have changed the function. The function is not the same. Why? We have added in 1 and we have added in 9. So if we want the function to be the same, we have to take out what we have added in. So we subtract a 1 and we subtract a 9. Now let's complete the square here. The first, that's a perfect square, and that is x minus 1 squared. This is a perfect square, and that is y minus 3 squared. And this is 4. Now let's see what's happening. What is that telling us? Beautiful. Well, let's see why. So somebody said it's a minimum, and he's right. Let's see why. This is a squared, right? So this is always greater than or equal to 0. Agreed? This is also a squared. So this is also greater than or equal to 0. And we're adding 4 to all of that. So that says that the function f of xy is greater than or equal to 4. 4 is the lowest value that that function can have. So this tells you that f of 1, 3 is a maximum. What am I saying? Sorry. I'll say it again. F of 1, 3 is a minimum. And it is actually the absolute minimum. It's not only local, it's absolute. Because this is the lowest point there. Okay? So let's write that. So f of 1, 3 is a local and absolute minimum. And the minimum value is 4. Okay? So that's number 1. So that's a little trick I showed you to find the minimum. You will not have to do that all the time actually, but it will help you to know these little tricks. Let me show you another trick. F of xy equals y squared minus x squared. Let's find the critical point and let's classify it again. So partial f with respect to x is minus 2x. Put it equal to 0, x is 0. Partial of f with respect to y is 2y. Put it equal to 0, y equals 0. So the critical point is 0, 0. And right away, find what f at 0, 0 is. Put it back into the function. We get 0. So let's see what we can do to determine what type of point this is. Right? What is it? Look at the function. Y squared minus x squared. There's nothing we can do with that. It's a difference of squares. Nothing we can do. We can't complete square. Nothing. So we have to try another method. All right? So look at what we're going to do. So remember, we are looking at 0, 0 within a disk. You with me? So what we are going to try to do is to see if we can find the values of f at any points within the disk, close to 0, 0, right? Now, the thing is, there are many points there, right? So you have to do that in a smart way. You cannot just choose, say, 0.1, 0.1, negative point. You know, you cannot do that. You have to do that in a smart way. So what I'm going to do is possibly hold the x value constant, right? X equals 0. Because remember, it's around here, right? Let's write what I'm going to do. So at x equals 0, so hold that constant. Good? And let y vary. So put x equals 0 into the function. What do we get? The function becomes f of y equals y squared, right? Which is always greater than or equal to 0. Right? So this is always positive. Are you with me? Now hold y0. What does the function become now? F of x equals negative x squared, right? Which is always greater than or equal to 0. So basically, we can say this. In the first case, if y is not 0, you know, let me just take out this equal sign for both of them. Why am I taking out the equal sign? Because I'm only holding x equals 0 constant. I want y to vary, right? I don't want y to be equal to 0 because I want it to be around 0, 0. So this is greater than 0 for y not equal to 0. The other one is less than 0 for x not equal to 0. What is happening? Some of the values are positive, right? Some of the values are negative. And we have 0 in the middle. So this tells you that 0 is not a max or min. It has to be a saddle point, because the points are varying. This is positive, negative, and 0 in the middle. So therefore, 0, 0 is not a max or min. It is called a saddle point. Now, you know what I want us to do now? I want you to see what a saddle point looks like and maybe what a min looks like as well. So why don't you take your calculator, and I want us to plot this graph, f of xy equals y squared minus x squared, so that you can have a look at what it looks like. So remember what to do here. You want to insert graphs. And you want to go to menu, and I think you want to go into view, if I remember, 3D graphing. Then enter y squared, what is it? Y squared minus x squared. Y, is this squared? Yes. Minus x squared, and then enter. Do you see it? This is the saddle point. You see it looks like a saddle? So if you turn it around, you'll see it better. You see? That is a saddle point. It's not a max or a min. You see it? So twist it and you can see it. You can sit on it. It's like a saddle. Okay? Now see, this other, the first one that we did, enter it in as well, and we got a minimum, right? So let's choose a new document. No, I want to save that. Menu, view, 3D. So enter x squared plus y squared minus 2x minus 6y plus 14. And enter. Oh, that's really small. But anyway, look at the minimum. You see? Right. It's right on top of there. Okay? All right. So I wanted you to see what this looks like before we continue. Any questions?
So the saddle points, they never have a max or a min?
No, a saddle point is not a max or a min. Okay, you all heard that? You cannot have a max or a min on a saddle point. It's like a point of inflection. You're right. Okay, let's move on. So let me teach you the second derivative test. So this is the one that you are, oops, sorry. Sorry about that. So this is the test that you are going to use to classify the critical points. But sometimes this test fails. When that test fails, you'll have to resort to some of the stuff that we just did. Okay? What is the second derivative test? Suppose that the second partial derivatives are continuous in a disk with center AB, and suppose AB is a critical point of F. So again, you must find the critical point. Define D to be the product of fxx and fyy minus fxy all squared. So here are the conditions. If D is positive and fxx is positive, then f of AB is a local minimum value. If D is positive and fxx is negative, then it is a local maximum value. If D is negative, then f is a saddle point. And if D is equal to 0, the test is inconclusive. That is where you go back to what we previously did. Now you may be wondering, where did this formula come from? We use Taylor series. You remember Taylor series for in single variable calculus? There's Taylor series for multivariable calculus. So that's what we use to get that. Okay? Alright, so let's use this. Let's start with some easy ones. Determine the nature of the critical points of f. Let's find the critical points. The partial of f with respect to x is minus 2x plus 2. Put it equal to 0. X is 1. The partial of f with respect to y is minus 2y plus 4. Put it equal to 0. Y is 2. The critical point is 1, 2. Right away, let us find f at 1, 2. That's minus 1, minus 4, plus 2, plus 8, plus 5. What is that? 10? Okay. So we are going to determine whether this is a local max or local min. We're using the second derivative test, so let's find all the second partials. fxx, so partially differentiate this with respect to x, that's a minus 2. fxy, with respect to y, that's a 0. fyy, partially differentiate this with respect to y is minus 2. Any questions on these second partials? We did these a little while ago. Now let's find D. D is the product of fxx and fyy, which is 4, minus fxy squared minus 0, which is 4. What do we see here? D is positive, fxx is negative, based on the second derivative test. So this implies that 1, 2 is a maximum, a local max. Sorry about that. Let's take out this max. A local max, maximum. And what we got, 10 is the local maximum value. Okay. So that one was an easy one, because there was only one point that we had to look at. But sometimes you can find more points. Let's do some more. Number 2. Let's find the critical points again. First partials. Partial of f with respect to x is 2x minus 3y. Put this equal to 0. There's nothing we can do here. Leave it alone. So let's call this 1. Partial with respect to y is 3y squared minus 3x. Put it equal to 0. And divide by 3, y squared minus x equals 0. Call this 2. Now, you have to solve these two equations, right? You would solve them by substitution. So you can take one and put it into the other. Whichever one. I think we can take in number 2, solve for x and put it into number 1. I think that's what I would do. Okay? So here x is equal to y squared. So substitute in 1. So 1 becomes 2y squared minus 3y equals 0. Now you can solve that. Factor out the y. 2y minus 3 is 0. So y is 0 or 3/2. Now take these 2 points for y and find what x is. So remember, x is y squared, right? So y is 0 implies that x is 0 squared, which is 0. Y is 3/2 implies that x is 3/2 squared, which is 9/4. So we have 2 critical points. Zero, 0, and 3/2, 9/4. Okay? Nice. Any questions so far? Pardon me?
Should 9/4 and 3/2 be switched around for that recording?
You're right. Yes, we have that incorrect, don't we? Thank you. Thanks. So this should be 9/4, 3/2. Okay. Now, let's test. We need the second partials, so let's do that. So they're right there. fxx, so you have fx up there, partially differentiated with respect to x, or 2. fxy, that's a minus 3. And fyy, what is it? 6y. Now this is what I would advise you to do when you have more than 2 points, more than 1 point. Draw a little table, because you'll have to find the values, all of these at the points, right? So this is what I would do. Draw a little table, and it's going to help you tremendously. So put your point here, the 2 points, 0, 0, 9/4, 3/2. Then the first column, put fxx and put the value. It's 2 we got, so put 2 and 2, right? Then you can put fxy. Let me put fyy because these are the 2 that we have to multiply together. Now fyy is 6y. Don't put 6y because you have to find what 6y is at the point. So at 0, 0, 6y is 0 because y is 0. At 9/4, 3/2, 6y is 3/2 times 6, which is 9. So you need to put that in. Then put fxy, which is -3, -3. Then put d. So calculate d. So remember what d is? The product of the first 2 minus this one squared. So 2 by that, that's 0 minus 9. So that's a minus 9. And 2 9s are 18 minus 9. That's a positive 9. Okay, what do we have here? D is negative, so this is a saddle point based on our conditions. And here D is positive and fxx is positive, so this is a local minimum. And in the last column, put what f of xy is. So take 0, 0, put it into the function, you get 0. Take the other point, put it into the function, you get negative 27 over 16. And you're done. When you set it up like that, it's going to be a lot easier for you. Any questions so far? Okay, let's move on. Number 3. We're doing the same thing. Let's go. Somebody give me the partial of f with respect to x, please. One person. Let's do it. 3 what? Uh-huh. Uh-huh. Good. Put this equal to 0. Now, if you can reduce. We can divide by 3, so let's do that. X squared plus y squared minus 2x is 0. Call this 1. Nothing we can do there, so move on. The partial of f with respect to y. Can somebody give me that one? Good. Put it equal to 0. Reduce. xy minus y is 0. Now this we can do something about. Why? So this is my point. If there's any of these two equations you can work with first, do that. You can solve. This we can solve. Why? We can factor out the y. And we have x minus 1 is 0. So this tells us that y is 0 or x is 1. So substitute into 1 now. Substitute in 1. So let's start with y equals 0. So put y equals 0 into 1. We get x squared minus 2x is 0. You can solve that. Factor out the x. X minus 2 is 0. So x equals 0 or 2. So all of this gives me critical points as 0, 0, 2, 0. So that's 2 of them. Any questions so far? Let's move on to x equals 1 now. Take x equals 1, put it in the first equation. 1 plus y squared minus 2 is 0. That tells me that y squared is 1. So y, when you find the square root, is plus or minus 1. We have 2 more critical points. 1, 1, and 1 minus 1. So we have 4 points to test. Any questions? So So these questions can be pretty long, but if you go about it in an orderly fashion, in a sequential manner, you'll be fine. Now let's find the second partials. So one person give me fxx, please. fxx. Don't look at the reduced one. 6x minus 6. Good. fxy. You partially differentiate in fx with respect to y. What's it? 6y. And what's fyy? 6x minus 6. Okay, let's draw up our little table. So you have the points here. We have 4 points. 0, 0, 2, 0, 1, 1, 1, negative 1. Put a column for fxx, another one for fyy, another one for fxy, another one for d, for the type of point, and then finally for f of xy. So you can put f of xy first, it doesn't matter. Okay. All right, let's do this. So fxx is 6x minus 6. For each of these points, let's substitute that into 6x minus 6 for x. So this is, what's the first one, anybody? Negative 6, next. 6, next. 0, next. 0. Good. And if you notice, fyy is the same thing, so put the same values down. fyy, now fxy is 6y. Tell me what these values are now. This one, first one, 0, 0, 6, negative 6. Now let's find d. These two product minus this one squared. So this is 36. Continue. 36. Continue. Minus 36 is this squared. Last one. Minus 36. Okay. The first one, what is it? Look at D. It's positive. So look at fxx. It's negative. So based on your notes, it's a local max. Next one, D is positive. fxx is positive. So it is a local min. The last two D's are negative, so it's a saddle point. And you'll have to put these points back into the function, and you know I don't have it. Okay, what is it? Well, 0 is easy. I think 0 gives me 4. 2, 0 gives me what? 2 is x, so that's 8 minus 12. You help me. Come on.
8 minus 12 plus 4.
Plus 4, that's 0. 1, 1. 3 plus 3 minus 3 minus 3 plus 4. That's another 4.
The first term would just
Some-
be 1.
Something is wrong here. That can't be 4 again.
Maybe 2.
So what do I have wrong there?
You did x cubed equals 3.
Oh, that's 1. Thanks. So that's 2. And 1 negative 1. What's that? So that's a 1. It's the same thing. 3 minus 3 minus 3 is the same thing. 2. Okay. I want to do one more and then you'll try one, okay? Number 4. Okay, one person give me fx.
6y squared
6y squared
minus 6x squared
minus 6x squared. Put it equal to 0. Reduce. Y squared minus x squared is 0. Good. Somebody else give me fy. 12xy minus 12y cubed. Put it equal to 0. Reduce xy minus y cubed equals 0. Right? Okay. We have a number of things we can do here actually. Actually, we can take any one of, let's call this 1 and 2. Any of these equations, you know, can be solved. So and I think number 1 is the easiest one to solve. Why? Because this tells me that x squared is y squared. So when you find the square root, x is plus or minus y. So I think that one was the easiest one to solve. And so substitute in 2. So x is y. Put that into 2. We get y squared minus y cubed is 0. Factor out y squared. 1 minus y is 0. So y is 0 or 1. But remember, x is y, right? They have the same coordinates. So y is 0 implies that x is 0. Y is 1 implies that x is 1. So this gives us critical points 0, 0, 1, 1. Any questions so far? Let's continue. We now have to substitute x equals minus y into the second one. So x equals minus y. Put that into the second equation. We have minus y squared minus y cubed is 0. Right? You can factor out minus y squared into 1 plus y is 0. Y is 0 or negative 1. X is minus y, so when y is 0, again x is 0. Y is minus 1, x is 1. So the critical point we have there, we don't need 0, 0 again, but we need 1 minus 1. So we have 3 critical points. Now that we have the critical points, what's our next step?
Or the second part.
The second partials. Good, let's do it. One person give me fxx
Negative 12x.
minus 12x, fxy
12y.
12y, fyy 12x minus 36y squared. Beautiful. Draw your table. Oops. Woo. We have a lot more work to do and I don't have much space. I think I wrote too big. What am I going to do here? Let me squeeze it in on that side, okay? So xy, we have 0, 0. We have 1, 1. we have 1 minus 1, fxx, fyy, fxy, d. Let me put fxy, and then we'll put the type of point, okay? So doing the same substitution, fxx, that is 0 minus 12 minus 12. fyy, which is 12x minus 36 y squared, that's a 0 minus 24 minus 24. fxy is 12y, 0, 12 minus 12. D ends up being 0, 144, 144. Oh, I did not calculate f of xy, did I? Let's leave that a little. We'll come back to that. Let's put the type of point. D is 0, so that is what? When D is 0, what? What did I say? Inconclusive. Test fails. So we need to use another test. D is positive and fxx is negative, so both of these are local maximum. Let's find f of xy there. What is that? Put 0, 0, that's a 0. Put 1, 1, that is 6 minus 2 minus 3. That's a 1 and that's a 1. Now the test fails. So that is where we need to go. And I would use, based on the type of function, I would look at this within a disk again. Okay, so so we test 0, 0 within a disk. So again, I would let x equals 0 remain constant. Put 0 into the function. We have f of y equals minus 3y to the 4th. And this is always less than 0 for y not equal to 0. All right, so that's the first test we go into. Then hold y equals 0 constant. What is f of x? It becomes minus 2x cubed. But what do you know about that? For x not equal to 0, that can either be positive or negative, which is positive or negative for x not 0. So therefore, what does that tell you about the type of point? What is 0, 0? Is what? There's only one thing it can be. Look at how this fluctuates. It's a saddle point. It moves up, it moves down. You don't know. So it's a saddle point. Okay, that one was a long one. But I wanted to do one with you where the test failed. Okay? Okay, try this one on your own, and then we'll go over it together. Okay, let's go over it together. Can one person give me fx, please? 2x plus y, put it equal to 0. Another person give me fy, please. And put it equal to 0. Can somebody tell me how you solve these two equations? Substitute which one? Okay, so you use y equals negative 2x and substitute in 2. Good. So this becomes, when you substituted, what did you get? Tell me. X minus 4x plus 1 is 0. So what did you get for x? 1/3. And this tells me that y is what? Negative 2/3. And it's just 1 point, so I would find what f of 1/3 negative 2/3 is. What did you get for that? Negative 1/3. Okay. What is fxx? 2. fyy. 2. fxy. 1. So what is d? 3. 2 times 2 is 4 minus 1, which is 3. What is your conclusion? Local min at 1/3 minus 2/3. Done. Any questions? Okay, let's continue. Let's do some applications. So we're going to do some word problems whereby we have to find extrema. And by the way, there are other ways you can work out these, which we will do later on in this chapter. But we can do these problems. They may be just a little longer. Find the shortest distance from the point 2, 0, negative 3 to the plane. Okay, what do we need to do here? We need to find a function for distance. This question is asking us for shortest distance. So we need to find a formula for distance and minimize it. Find the minimum value because it talks about the shortest distance. But what kind of formula are we looking at? We need to choose an arbitrary point in the plane and find the distance between the point 2, 0, negative 3 and an arbitrary point in the plane. Okay? So, I'm going to say, let x, y, z be an arbitrary point in the plane. Now let's find the distance between x, y, z and 2, 0, negative 3. I hope you remember how to find the distance between 2 points. It will be the square root of the sum of the difference between, the sum of squares was the difference between the numbers. So let's look at is the square root. I didn't say that well, but I prefer to write it then. So that would be x minus 2 squared plus y minus 0 squared plus z minus 3 or z plus 3 squared. But this is a function of 3 variables here, right? When writer, you only know how to find extrema for a function of 2 variables. So I need this to only have x and y and not z. How do I do that? Here is the clue. The arbitrary point x, y, z lies on the plane. So it satisfies the plane. So this is what we're going to do. But x, y, z lies in the plane x plus y plus z equals 1. So this implies that z equals 1 minus x minus y. We solve for z. Now take the z value and put it into that square root function. So we get square root of x minus 2 all squared plus y squared plus z 1 minus x minus y plus 3 squared. And when you work that out, we'll leave this as x minus 2 all squared plus y squared plus 4 minus x minus y squared. So we have our function. So we wish to minimize f of xy. Now there's a little trick. Our distance has the square root thing, right? Now I don't know about you, I certainly do not want to find the first partials of that function there. It's crazy. It's going to be crazy. So there must be an easier way. Minimizing this square root function is the same thing as minimizing it without the square root. The minimum of this with the square root is similar to finding the minimum of it without the square root. So remove the square root. So minimize, that's a trick. X minus 2 all squared plus y squared plus 4 minus x minus y squared. Now this I wouldn't mind finding the partials for. See, it still looks a little strange, but it's better than the square root thing, okay? Okay, so let's do what we have done before. Find the first partials. Any questions so far? Partial of f with respect to x. So this is 2 times x minus 2. Then we have a 2 times 4 minus x minus y. There's a minus x, so let's put that minus here. And I would advise you to simplify that. When you simplify that, you get 4x plus 2y minus 12. Put it equal to 0. 4x plus 2y minus 12 equals 0. Reduce 2x plus y minus 6 is 0. Call this 1. Fy is 2y, and you get a minus again, 2 times 4 minus x minus y. Simplify again, 2x plus 4y minus 8. Put it equal to 0. Reduce x plus 2y minus 4 is 0. Any questions so far? Now this is an ordinary system with two variables. We can do that. So let me just write out the solution. We've done quite a lot of that today. So I'm just going to say solving 1 and 2. You get that x is 8 over 3, y is 2 over 3. And then right away, f of xy, you can put that into your function, and you get 4 over 3. Now we need to show that it's a minimum. We only got 1 point, so it has to be the minimum. But let's just test it. fxx, that leaves us with 4. fxy, that leaves us with 2. fyy, that is 4. D is 16 minus 4, which is 12. D is positive, fxx is positive, so there's a local minimum or minimum at 8 over 3, 2 over 3. The question is asking us for the shortest distance, isn't it? So the shortest distance would be your minimum value. But remember, we removed the square root. We need to put it back now. So the shortest distance is now the square root of 4/3. So So you put it back at the end. Interesting problem. Any questions? Okay.
Question for you.
Yes.
Your square root 4/3 there, that's the result of substitution in all the terms you have in the equation.
Yes. Above. Okay, so I substituted 8/3 2/3 into the function, and I got 4/3, but square root, so you put the square root. Okay, next one. Now, a question like this should be familiar to you, but we're now in functions of several variables, so I think when you did that in single variable calculus, the box had a square base. Now it doesn't. A cardboard box without a lid is to have a volume of 32,000 cubic centimeters. Find the dimensions that minimize, again, the amount of cardboard used. Let's draw the box. Give the box some dimensions. X, Y, Z. It has no lid. Now we need a function. What do we have to minimize? The amount of cardboard used. The amount of cardboard used would be what? No, I'm not asking, let me rephrase that. I'm not asking you for a number. What does that mean, amount of cardboard? What does that have to do with the... It is, I know it's a minimum, but what is the function? What do we have to calculate? Surface area. Beautiful. So, the surface area, remember it has no lid, right? So the area of the bottom is XY. The area of the front is XZ. There are actually two, and there are two YZs. Okay? But that's what we have to minimize, but again it has three variables. So we need to put it in terms of X and Y, so again we need to make a substitution. In the question, the box has a volume of 32,000, right? So that tells us that X, Y, Z is 32,000, which means that Z is 32,000 over XY. So put that into the surface area here and call it f of xy. Okay, so let me just rewrite surface area. So that is xy plus, how can I put that and make it easier? Okay, let's just put it as 2x times 32,000 over xy plus 2y times 32,000 over xy, which is xy plus 64,000 over y plus 64,000 over x. So that's a function. So we wish to minimize f of xy equals xy plus 64,000 over x plus 64,000 over y. Alright, so as long as you have your function, you're good to go. That is what you need, okay? Alright, let's find the first partials. The partial of f with respect to x, that leaves us with y minus 64,000 over x squared. Put this equal to 0. Y minus 64,000 over x squared is 0. Call this 1. Partial of f with respect to y. X minus 64,000 over y squared. Put this equal to 0. And that's 2. Okie dokie. So you know, we need to do some substitution here. So what I'll do, I'll solve for x here and put it into here. Okay? So x is equal to 64,000 over y squared. Substitute in 1. We could have done the other, but it doesn't matter. Y minus, okay, this is 64,000 divided by x squared. So x squared over there would be y, 64,000 squared over y to the 4th. We're dividing by it, so let's invert. Y to the 4th over 64,000 squared. And that's 0. Okay, what do we have here? Y minus y to the 4th over 64,000 equals 0. Okay, we can do a number of things here, you know. Let me get rid of this fraction. 64,000 y minus y to the 4th is 0. Now let's factor out y. 64,000 minus y cubed is 0. So y is 0, or y cubed is 64,000. So y is a cube root, which is 40. Uh-oh. I'm going to go here, okay? Now 0 does not make sense because you'll have no box. So use y equals 40. So when you use y equals 40 and you substitute it into any of the, either the equation 1 or 2, you'll get x is 40. Okay? Now let's find fxx, which is 128,000 over x cubed. fxy 1, fyy 128,000 over y cubed. I have no space to draw my little table, so I'll just tell you what d is, okay? D is going to be positive. Fxx is going to be positive. So this means it is a min. And what is the question asking again? The dimensions? Okay, so the dimensions would be 40 by 40, and you need to find z, which is 20. So this tells me you can work it out that z is 20. Put it back into xyz 32,000 and you'll get 20. Okay. Alright, so these are applications, and later on I will show you another way to do this. The last thing we will do is global, max, and min. We have a number of theorems, and I've actually stated the steps for these absolute extrema. If f is a continuous function on a closed and bounded region, it has to be closed and bounded, then f has a global or absolute maximum at some point in R and a global minimum at some point in R. So as long as you have a closed and bounded region, there must be global extrema in there. What do we know about this extrema? Suppose that F is continuous on a region, that if F, there's something missing there. Okay. I would put, suppose that F is continuous on a region R and, consisting of the points on or within a simple closed curve C. If AB is an absolute extremum, then AB is either an interior critical point or it's on the boundary. So the absolute extrema only occurs inside the region or on the boundary, nowhere else, okay? So these are the steps to finding the absolute. Do the same thing. Find the first order partials and the critical points. Find the extreme points on the boundary. List the endpoints. Find the value of the function at all of these points. The highest value is the absolute max. The lowest value is the absolute min. Okay, the best way to understand that is to do examples. So we have a few that we can do. Okay, let's do this. Number 1. Find the global extrema attained by the function on the region R, which is this, and you have the function and it's a square with vertices plus or minus 1 plus or minus 1. Draw the square so that you can see it. Okay, so -1 is not very accurate, but I think you get the picture. Okay? All right. The first part is very familiar to you. Find the partials, just find the critical points. First partial, fx is 1. Now, remember we have to put this equal to 0. That cannot be 0. What about fy? It's 2. That cannot be 0. So there is no interior critical point. So that's an easy one. So nothing is happening on the interior. So the next thing, after you have done that, check the boundary. Now what do we mean? So on the boundary we need to find the critical points. So if you look at the square, the boundary is made up of 4 lines, right? So you need to take each line in turn and put it into the function. So let's start with x equals 1, the one on the right. So x equals 1. So take x equals 1 and put it into the function. So it becomes f of x equals 1 plus f of y, f of y equals 1 plus 2y. This is now a function of one variable, right? Go back to single variable calculus. Find the critical point. So find the derivative, f prime of y. You get 2, put it equal to 0 and solve. Another example, that cannot be 0. No critical points here. Next one, y equals 1. Or let's do x equals minus 1. Let's take out the x's, so put the 1 on the opposite side. Put it again into the function. F of y is minus 1 plus 2y. F prime of y again is 2, not 0. Okay? Let's do the y's now. Y equals 1. F of x is x plus 2. F prime of x is 1, not 0. We cannot do anything here. Y equals negative 1. F of x is x minus 2. F prime of x is 1, not 0. So we have no extrema on the boundary. So we can't do anything there. No extrema on the boundary. So therefore, what do? Remember, either the critical points on the boundary or the end points. So use the corners of the square now. That's what you're going to check. So use the end points. Okay, so what you're going to do is to find the value of the function at the end points. The highest value is your max. The lowest value is your min. So I think let's draw a little table again. So put the point. I'll put the point on the top. So there are 4 vertices. There's 1, 1. There's minus 1, minus 1. Minus 1, 1. There's 1, minus 1. And f of xy. Now f of xy is x plus 2y. So take all of these points and put it into there. So x plus 2y, this becomes a 3. X plus 2y minus 3. X plus 2y 1. X plus 2y minus 1. So the highest value is 3. So here is your global max. Your lowest value is negative 3. Here is your global min. So that's the first one. So they are not as easy as that. That was easy because we only use the endpoints. So let's do some others. Number 2. F of xy is x squared plus 2y squared minus 2x, and R is the triangular region with vertices at 0, 0, 2, 0, 0, 2. Let's draw that region. Zero, 0, 2, 0. There's something missing there. 0, 2. That's not what I want. Hold on a minute. No, that's right. Thank you. That's right. I was looking at something else. So this is the triangle you want, okay? Let me draw that in blue so that in red. Okay, so this is 2, 0, 2. Okay, let's start. Let's find the first partials. Fx is 2x minus 2. Put it equal to 0. X is 1. Fy is 4y. Put it equal to 0. Y is 0. So the critical point is 1, 0. And always check when you get the points that they are either in or inside the region or on the boundary. And I think it's on, so that's good. Alright? That's the first step. The next step are the boundary points. Let's check the boundary now. Boundary. So this horizontal line is the x-axis. So it's x equals 0, y equals 0, sorry. We have to do x equals 0, but that's okay. So take y equals 0 and put it into the function above. So it becomes f of x equals x squared minus 2x. So what are we doing? We are finding extrema. So find the derivative, 2x minus 2. Put it equal to 0, and you get x equals 1. So the critical point again is 1, 0, because y is 0. So we have that already. Next boundary, let's take the y-axis, which has equation x is 0. Do the same thing. Put it into the function. F of y equals 2y squared find the derivative. F prime of y is 4y equals 0. We get y is 0. So our critical point is 0, 0. And that works. It's right on the boundary. Good. We have one more line to find. We need the equation of this line. So you have to go back to your algebra. And you can easily find it because the slope is minus 1. So it's minus x. The y-intercept is 2. So it's plus 2. So now we check in at y equals minus x plus 2. Take this and put it into the function. So we have f of x equals x squared plus 2 times minus x plus 2 squared minus 2 times minus x plus 2. Put it into the function. And now I would advise you to simplify that. When you simplify that, you get 2x squared minus 6x plus 4.
Why did we put negative x plus 2 in the last part?
The last part has a y, not a y?
Just negative 2x.
Oh, it's just, okay, sorry, I'm looking at the wrong thing again. Thank you. Thank you very much. Okay. Good, thank you. The derivative of this is 4x minus 6. Put it equal to 0. That gives me x equals 3/2. And when x equals 3/2, what is y? So take this and put it into here. So this implies that y equals minus 3/2 plus 2, which is 1/2. I made a mistake? Tell me where it is.
The negative x plus 2 to square that,
Mm-hmm.
and then you multiply by 2, and you add that to the first term x squared, and you get 3x squared.
I get a 3. You're right. You're right. Thank you for pointing this out. That is right. Okay, so that, do you have the answer?
No, I just
Okay, let's simplify that again. We have an error here. Oops. What did I have here? X squared? So this is x squared. Let me just work that out. Let's just do it. X squared plus. So that's an x squared times 2, 2x squared. Minus 4x times 2, minus 8x. 4 times 2 plus 8, minus 2x. So we have 3x squared minus 10x plus 8. Is that right now? Yeah, that looks good now. F prime of x is 6x minus 10. Put it equal to 0. So x is 5/3. And then put this 5/3 into this y equals minus x plus 2. Y equals minus 5/3 plus 2, which is 1/3. So your critical point is 5/3, 1/3. Okay. Any questions so far? These questions are quite long. So we have checked the interior, we have checked the boundary, we now need endpoints. So now we can draw a table, but don't forget to use, I'm going to put that because people always forget that you have to use the endpoints. Let's draw the table. XY, f of xy. Okay, what did we find? We found 1, 0. We found 0, 0. We found 5/3, 1/3. And the endpoints are 0, 2, 2, 0. And that's it. Now take your original function and take all of these values and put it into the function. So I can just write that down for you. You have a minus 1, a 0. This is minus 1/3. This is 8. This is 0. This, the highest one, global max. The lowest one, global min. Okay, 2 more. I put quite a few problems because I found in teaching this over the years, this was the problem in this section a lot, especially when I gave the exams. This is the one that students really scored poorly on. So I put quite a few so that we would get the hang of it, okay? Number 3. F of xy is 2x squared minus y squared plus 6y. And what is the region? A disk. Radius 4. So let's draw it. Negative 4 and 4. It's a circle. Now, this has no endpoints. How do we handle that? But there's a boundary. Okay? So let's try this out. Let's find the interior. We have no choice. We have to do the first partial. So let's do that. Fx, 4x. Put it equal to 0. X is 0. Fy minus 2y plus 6. Put it equal to 0. Y is 3. So the critical point is in the interior, 0, 3. We good here. Boundary. Now the boundary is the actual circle, and so the equation is x squared plus y squared is equals 16. So it's a circle, it has no straight line, so we have to use this entire equation and put it into the function. Okay, so because you see the type of the function, there's a y squared and there's a y, I would substitute for x squared. So x squared equals 16 minus y squared. So substitute into function. So the function becomes f of y equals 2 times 16 minus y squared minus y squared plus 6y. And when you work that out, I work that out, and we get minus 3y squared plus 6y plus 32. And by the way, this only occurs, now you have to do that for this question. This only occurs between negative 4 and 4 on the y-axis, nowhere else. So put this for y between negative 4 and 4. I'm doing that because it's the circle. There are no straight lines, you see? So you have to have some kind of bounds. Okay, do the same thing. Find the derivative. F prime of y is minus 6y plus 6. Put it equal to 0. Y is 1. Take this y equals 1 and put it into the x squared equals 16 minus y squared. And so this tells me that x squared is 16 minus 1, which is 15. So x is the square root of 15 plus or minus. That's about 3 point something, so we're still inside the circle. So here we have two critical points. Square root of 15, 1 minus square root of 15, 1. And now, based on, remember we chose f of y for y between negative 4 and 4. We are going to use these as the endpoints. Okay, because we chose that particular function. So the endpoints we are going to use are 0, minus 4, and 0, 4. So it's right on the y-axis. Okay, so we have 5 to check. Okay, let's do it. Draw the point f of x, y. So we have 0, 3. Square root of 15, 1. Minus square root of 15, 1. 0 minus 4. 0, 4. Put these points into your function. We get 9, 35, 35, negative 48. These are the highest, so that's your global max. This is the lowest, so that's your global min. One more. Last one. So notice we have the same square that we had a while ago. So let's just draw it. Okay, let's go. What's the first thing? You tell me, we're doing it together. What's the first thing to do? Find the partials. Partial with respect to, yes, and set them to 0. So this one is 2x minus 4xy. Let's reduce this a bit. 2x minus 4xy equals 0 tells me that x minus 2xy equals 0. And fy gives me 8y minus 2x squared equals 0. Reduce. 4y minus x squared is 0. Call this 1, call this 2. Now you can do that. There's so many things you can solve that in so many ways. Let's find what y is here. Y is x squared over 4 and substitute into 1. Well, we should not have reduced, you know, because we're getting a fraction now. But anyway, we did it already. Put y equals x squared into this reduced one. So x minus 2x times x squared over 4 is 0. X minus x cubed over 2 is 0. Factor out x. 1 minus x squared over 2 is 0. So this implies that x is 0 or x squared over 2 is 1. X squared is 2. So x is plus or minus square root 2. So we have quite a few points. Interesting. So we have 3 values for x. For each of these, we need to find what y is. So put it into y equals x squared over 4. So x is 0 implies that y is 0. X is plus or minus square root 2 implies that y is, put it into x squared over 4. That's 2 over 4, which is 1/2. So our critical points are as follows. 0, 0, positive square root 2/2, minus square root 2/2. All right. So let's just check. Oh, I think all of these. No, I'm glad I'm doing this question. There are 2 points that we cannot choose. Anybody can see why we should ignore 2 of them.
Square root of 2 is bigger than 1.
Very good. Square root of 2 is 1.4. That is outside of the region. So we need to ignore them. So these 2 are outside of the square. So ignore. I'm glad I'm doing this. Okay. Boundaries now. I think I'm going to run out of space again. Boundaries. So let's take x equals 1. Put it into the function. We have that f of y equals 1 plus 4y squared minus 2y plus 4. So that is 4y squared minus 2y plus 5. Next step. Find the derivative. 8y minus 2 is 0. So y is 1/4. So the critical point here is 1/4. Do the same thing. We have 3 other lines. X equals minus 1. F of y equals 1 plus 4y squared minus 2y. Oh, that's the same thing. Notice? It's the same above. So we're going to get y equals 1/4 again. So your critical point is minus 1 1/4. That saves us a little space. Next line. Let's do the y's. Y equals 1. F of x equals x squared plus 4 minus 2x squared plus 4, which is equal to minus x squared plus 8. Find the derivative. Minus 2x equals 0. We get x is 0. Oops. Ay, ay, ay. Uh-oh. I'm going to write on this page, okay? I hope it will save. So critical point is 0, 1. Y equals minus 1 gives us f of x equals x squared plus 4 plus 2x squared plus 4, which is 3x squared plus 8. So f prime of x is 6x, which is 0. So x is 0. Critical point is 0 minus 1. How many we have so far? Wow. We have 3 critical points. Now what do we need? What's the last thing we need? We've done the boundary. We need the endpoints. So we'll just put them into the table, okay? So use endpoints. Okay, draw the table. X, Y. Okay, what is the first point we got? 0, 0. Then we got something with a quarter, right? Minus 1 1/4. 1 1/4. Then we just got 0 1. 0 minus 1. And we have 4 endpoints. 1 1. 1 minus 1. Minus 1 minus 1. Minus 1 1. Wow, how many? 1 2 3 4 5 6 7 8 9. My word. Okay. Put this into the function. This is 4. This is 4.75. 4.75. 8. 8. 7. 11. 11. 7. Okay, what's our global max? The 2 11s, these two. Global max. And what's our global min? 4. Global min. Finito.
What a problem.